Hi everyone, in this video I'd like to work through finding some inverses for exponential and log equations. I think this is a great thing to do toward the end of our work with logs because it ties together a bunch of what we've done. So we'll have to solve exponential and log equations in order to find the inverses. We'll have to use log properties in order to do some of that solving and also in order to do some of the checking. Do you really get back x when you compose your function and its inverse? And then there's also some sketching of exponential and log functions involved. So let's get into it with this one. Here we're starting with an exponential equation. F of x equals 3 times 2 to the x minus 1. If we would like to find a formula for its inverse, let's go ahead and say x equals 3 times 2 to the y minus 1 and solve for y. There is only one y on one side of the equation, so this is going to be reverse order of operations. If I were to pick a number and plug it in for y, the order would be subtract 1, exponentiate with that base of 2, and then multiply by 3. I want to reverse that, so I'm going to divide by 3. I'm going to next try and get rid of the exponential base 2, which means take the log base 2 of both sides. It will cancel out nicely on the right and just leave me a y minus 1. And then I need to add the 1, so it looks like f inverse is going to be log base 2 of x over 3 plus 1. It didn't ask here, but I think I want to say domain restrictions now because I definitely ask later. So for the original function, the domain is all real numbers. You can plug anything you want into an exponential. For this new one, we need x over 3 to be strictly greater than 0, which means x has to be strictly greater than 0. Okay, so the checks. We want to find f of f inverse. Hopefully we're getting back x. And then we're going to talk about domain restrictions on that. F inverse was the log base 2, x over 3 plus 1. Okay, so f of that is going to be 3 times 2 raised to my entire input, log base 2 of x over 3 plus 1 minus 1. So you can see all the pieces of f, 2 to our input minus 1 multiplied by 3. Our input was the inverse function. First thing to go here is the plus 1 minus 1. Those happen one right after the other, so that's going to cancel out. I'll be left with the 3 times 2 to the log base 2 of x over 3. Order of operations now is take an x, divide it, take the log, exponentiate. So those two are right next to each other and will wipe out. So it looks like we are, in fact, getting back our x. If we want to talk about domain restrictions on the composition, we need to go back and check that inner function. So the inner function was the log function, which means x does have to be greater than 0 if this composition is going to get me back where I started and not just tell me undefined. We should be able to check the other direction as well. So now we want to take f inverse of the function, 3 times 2 to the x minus 1. Here, I'm going to move it down here. F inverse is going to take whatever I give it, 3 times 2 to the x minus 1. It's going to divide it by 3. It's going to take the log base 2 of that, and then it's going to add 1. Here, the first thing to go is the 3. Leaving me with log base 2 of 2 to the x minus 1. The next thing to go will be the log base 2 and the exponential base 2 wiping each other out. So we just get x minus 1 plus 1, which is just x. Perfect. This time the exponential function was the inner function, so this is actually true for all real numbers. It doesn't matter what x you start with. This will always work. If you plug it into f and then f inverse, you'll get back the x you started with. Okay, last part on this one is to sketch the function and the inverse, state the domain and range of each. So the function is a 3 times 2 to the x minus 1. So I'm picturing a 2 to the x, which has a horizontal asymptote at y equals 0, goes through the point 0, 1, and 1, 2. And the transformations that are being applied are a vertical stretch by a factor of 3 and a shift to the right by 1. So if we follow our horizontal asymptote and we do y's multiplied by 3 and then take our x's and add 1, the horizontal asymptote, if we do vertical stretch, it does not move. Everything stretches away from the horizontal asymptote. And then shifting that whole thing to the right also won't make it look any different. So we still have a horizontal asymptote for our exponential function along y equals 0. If I take the point 0, 1 and do vertical stretch, it will land at 0, 3. And then if I shift it to the right one, it will be at 1, 3. If I take the point 1, 2 and do vertical stretch, it lands at 1, 6. If I then shift it to the right, it will be at 2, 6. Okay, so let's see. This is going to go something like that. Okay, so there's the exponential function. There's more than one way to get the log. These are inverses, so the log should just look like a reflection across y equals x of the exponential function. I'm going to actually walk through the transformations on the log and then verify that they're inverses by making sure it looks like they're reflected across y equals x. But remember, that is an option. We could just flip this across and say, okay, the log should look something like this. So the log function has a vertical asymptote at x equals 0. It's a log base 2, so it will go through 1, 0, and 2, 1. So again, we have this inverse thing happening. It's the inverse of the original exponential function. We are then supposed to shift up 1 and stretch horizontally by a factor of 3. So our x's all get multiplied by 3, and we're going to add 1 to our y's. Okay, so the vertical asymptote, I stretch away from that, it doesn't move. I shift up 1, it doesn't look any different, so this is good sign. We had a horizontal asymptote y equals 0 on the original function, so we were expecting a vertical asymptote x equals 0 on the inverse. The point 1, 0, if I triple my x, it lands at 3, 0. If I then shift up, it lands at 3, 1. Again, this is looking great. I had 1, 3. I'm getting 3, 1. If I take the point 2, 1, triple the x, horizontal stretch, I get 6, 1. And then I move up, it's at 6, 2. Again, perfect. I had 2, 6, and now I have 6, 2. So the log function looks something like this. And they do, in fact, look like inverses, which is a good sign. All right, thanks for watching.